Hello everyone. In this session, let me continue with the next concept. In the previous session, you have learned that mu, a collection of measurable set mu, is a sigma algebra. Fine, I have done this theorem. Please go through that. Now, the next concept is borel sets. At least you will get 2 questions from this concept of borel sets. Maybe it may be asked for a sub question, like tag questions. You will get 2 sub questions in the concept of the borel set. Now, borel set is none other than, suppose if I have a sigma algebra, fine, if this sigma algebra is generated by all the open sets in R, then the members of this smallest sigma algebra is called as borel set. Or else I can say the members of the smallest sigma algebra which is generated by all the open sets in R. Let me repeat once again. Borel set is none other than the members of smallest sigma algebra, whatever the members is there in the smallest sigma algebra, which is generated by all the open sets in a real number R, is called as borel set, and it is denoted by B. Fine. And remember, all the open intervals and all the open sets, so open interval in the sense IN and all the open sets O is closed, is one of the example for a borel set. And also I have done G delta set and F sigma set. I hope you remember this. So union of all the closed set and intersection of all the open sets, right? So G delta and F sigma set is also an example for borel sets. You just remember this. Now, next is a very important theorem, and the statement is, every borel set is measurable. Every borel set is measurable. To prove this particular theorem, we have to prove one lemma. After proving this lemma only, you can go to the proof. So when they asked you to prove this theorem, you have to write the lemma. Lemma is it is a supporting statement for the given proof. Fine. So we have to prove the interval, open interval A infinity is measurable. Fine. We have to prove that the open interval A infinity is measurable. Before going to prove this theorem, let me revise some basic concepts of open and closed interval. Now, you are familiar with real number, right? So in real number, minus infinity will be the last number and plus infinity will be the positive highest number. So remember, when I'm going to take any point A on a real number, and this is just a basic, and you need to know this concept in order to prove the theorem. So if I am going to take any number, say A on a real number, this interval, this length we can represent as open interval A infinity. Remember, when I said open interval, it may not include the end values. When I said closed interval, it will include the end values. Difference between open and closed interval is that when I said open interval, end values will not be included in that. Fine. And similarly, if you're going to represent this portion including A minus infinity. Clear? Remember, any value on a real number, if you're going to choose like A, you can represent this length by A infinity, whereas this length I can represent, that should include an interval A. Fine. So A to minus infinity. Remember, I can say this length, that is A infinity length, complement will be equal to minus infinity A. In the sense, this length complement will be equal to this length. So what I have written is complement of this interval is equal to this value. So A infinity complement is equal to minus infinity A closed interval. Clear? You have to remember all these key points. Fine. Now, you can note that, suppose if you are going to take intersection of these two interval, what you have here? A infinity and minus infinity, open interval minus infinity, closed interval A. If you are going to take in intersection of these two sets, or these two intervals, whatever may be the case. So intersection in the sense, a common element you are going to list. Do we have any common any element between these two intervals? Clearly it is visible in the number line itself. There is no common interval between these two intervals. When I said A to infinity, it start with this point and end with this point. When I said minus infinity to A, it includes A and it goes up to minus infinity. Since we don't have any common point or any common element between these two intervals, so this intersection is always equal to null set. I am next going to take these values directly, so that is why I am explaining the basics. Fine. So if you're going to take in intersection, you're going to get null set. Suppose if you're going to take union of this interval, what you're going to get, you can clearly guess you are going to get a real number, right? So old number line minus infinity to plus infinity will represent a real number line R. Fine. And remember, I have already told you when you're going to take intersection, you have to write a second set. But it is not the case when you're going to take intersection with the open intervals. So when you're going to take open interval intersection with any real number, remember you're going to get the open interval in. Fine. Now, and the next thing is, any open interval AB can be written as minus infinity to B intersection A to infinity. Remember, any open interval AB can be expressed as minus infinity to B intersection A to infinity. These are all the key points that you should know to solve the theorem. So remember, a complement of open interval A infinity will be minus infinity closed interval A. So that is what I have written here. Similarly, when you're going to take intersection, as there is no common element, you're going to get null set. When you're going to take union, as it contains the whole real number line, so I'm going to write R. And remember, when you're going to take intersection with the open intervals on real number, you're going to get an open interval itself. And any open set AB can be expressed as intersection of these two sets. Clear? Now, coming to the proof of this theorem. I have already told you, to prove this particular theorem, I have to prove the lemma, that is A infinity is measurable. Fine. So let me go to the proof. So what we have to prove is A infinity is measurable. That is, as per the definition of measurability, I have to show that there exists one set A which is subset of a real number in such a way that m star of A should be greater than or equal to m star of A intersection this set plus m star of A intersection its complement. This is what the definition of measurability is. I have already told you. When do we say any set E is measurable? When there exists any set A which is subset of or such that m star of A will be equal to m star of A intersection this set E plus m star of A intersection this set's complement, that is E complement. This is what the definition of measurability of a set is. That this concept I have explained n number of times. So I have applied the same concept here. I have to prove instead of A, E, I have to prove A infinity is measurable. So that is why I have written A infinity here. So this is what I have to prove. Fine. Now let me take A1 as A infinity, A intersection A infinity. So this whole thing I have assumed as A, and let me take A2 as A intersection A infinity complement. So just now I have told you its complement I can write as open interval, minus infinity, open interval minus infinity comma closed interval A. Just now I have told you, see this, complement of A infinity is equal to minus infinity closed interval A. So that is what I have written here. See here, complement of A infinity is minus infinity A. So minus infinity A I have written. So A2 is equal to A intersection minus infinity A. Fine. Now let me take this statement as, so with this m star of A will become m star of A1 plus m star of A2. Clear? Let us assume this as equation 1. Suppose that if m star of A is equal to infinite, that is it is not countable set. In the sense, this value is infinity, this result is holds good, right? So infinity is always greater than or equal to any value. So there is nothing to prove. Equation 1 holds as it is. Fine. Now let us assume that m star of A is less than infinity. If that is less than infinity, I have told you while explaining the properties of measure of a set, that is outer measure or Lebesgue outer measure, if m star for a finite set, that is m star of A less than infinity, then there will be existence of epsilon, right? Epsilon greater than 0, such that I can write by the first property A can be expressed as subset of n is equal to 1 to infinity union of all the open intervals. This is from the property 1. I have not mentioned all these things in the notes. It is just for your reference. Fine. So A is subset of union n is equal to 1 to infinity and this is from the property of outer measure, that is property 1. And moreover, by the translation invariant property at the beginning itself I have mentioned length of in will be less than m star of A plus epsilon. Look at the notes. You just revise the notes. I have written this property at the beginning of a translation invariant. So if m star of A is less than infinity, then these two property holds good. Epsilon greater than 0, translation invariant property and property 1. As per that I have written this. Now let me take this as equation 2. Now what I am going to do is, let me set in complement, any open interval in, its complement as in intersection a infinity, and in double complement as in intersection minus infinity comma a. So that is what, in place of a1 what I have assumed is, I am explaining this is for with reference to open set a, this is with reference to open interval in. Fine. So what I have assumed is in complement as in intersection a infinity. In place of a I have replaced in place of a1 I have replaced i1 complement. Similarly, in place of a2 I have replaced an double complement. Whatever is there I have written as it is. Instead of open set I have proving this for open interval. Fine. Now if this is the case, I can clearly write a1 as a intersection a infinity. This is what I have assumed. So let me consider that. Now from the property 1, I am using this in this, so that you are going to get a1 will be clearly subset of union n is equal to 1 to infinity in. So this is what I have assumed by the property 1. So let me replace for a intersection with a infinity. Now I'll rearrange the term in such a way that anyhow it is for finite. So n is equal to 1 to infinity in intersection with a infinity. So while explaining the properties, I have told you a number of times. I can rewrite this as, see here a1, right? So a1 is subset of, now look at this value. Let me write this as it is, n is equal to 1 to infinity. I can replace this with in complement. See here, this value I have chosen as in complement. So I can write this as in complement. Fine. Similarly, by the same method, let me take a2 and I can prove that a2 is subset of union n is equal to 1 to infinity. You will get this set. So in double complement. Clear? What I have done is, I have assumed this statement once again. As per the property 1, I have replaced a with this. As per the, just I have rearranged. As per the property of intersection, when you are going to apply intersection, you have to take the second set. Instead of that, what I did is, all term can be replaced by in complement. This is what I have. Since I have obtained a1 as subset of this first interval, similarly I can prove that a2 is subset of the second interval. Fine. Now what I am going to do is, let me apply measure on both sides, so that you will going to get m star. When you apply measure on both sides, as per the monotonic property, this subset will become less than or equal to. So m star union n is equal to 1 to infinity in complement. I will change this in very next step. Similarly, see here, first let me simplify this fully. M star of a1 is less than or equal to, measure is none other than, or let us write one more step. So I am going to take measure inside. As per the theorem, this union will become summation n is equal to 1 to infinity m star of in complement, right? So instead of writing this, shall we write this as length of an interval? Why? Because I have already proved one theorem that measure of any interval will be equal to length of the interval. I have proved this theorem. Please go to the statement. Measure of any open interval will be equal to length of the interval. So by using that property, I can write measure of a1 is less than or equal to n is equal to 1 to infinity length of in complement. Fine. I have used the statement of theorem and I have written this. Now let me take this as equation A, just for your reference. So similarly, what can I write as m star of a2? By applying the same procedure for this set, I can write, no need to write again, just write as it is. I can write length of in whole complement. Let me take this as equation B. Fine. This is what I have. Now what I'm going to do is, let me keep this equation as it is. Now let me consider in complement union in double complement. Why I am doing all these things is, I am going to just replace these values further. In the further proof, I am going to get all these values. So that is why I am simplifying in the beginning itself. So in complement union in double complement I will take. So what I have assumed in complement as, let me write it as in intersection a comma infinity. Why? Because in complement I have assumed here. Now union with in double complement I have taken as in intersection minus infinity comma a. I have already chosen this. I have substituted. Now let me rearrange this so that you are going to get, I will group this. Anyhow you have intersection. When you have intersection, I can group. Instead of simplifying each and every number, I am going to simplify once at a time. So I can rewrite this as union with minus infinity comma a. Fine. Why? Because as I already told you while explaining at the beginning session itself, remember when you're going to take intersection with any open interval, you're going to get open interval itself. So that as per that property, I can write like this. So now see here, when you're going to apply intersection, you will get open interval only. So I'm going to take this set and this set separately. Now I have told you at the beginning itself that R can be expressed as union of A infinity and minus infinity A. So that is what you have here. See here, A infinity and minus infinity A I have, and union can be written as R, real number R. So let me write this as real number R. Intersection real number R. Again applying the property In intersection R is In. So what I have obtained is In complement union In double complement is equal to In. Clear? Now let me assume let me calculate its intersection. What I have calculated is its union is equal to In. Now let me calculate intersection. Whatever the value is there, just substitute. Here I have assumed, see here, In complement and In double complement is there. Just I am replacing the values here. In intersection A infinity intersection with In intersection minus infinity comma closed interval A. This is what I have assumed is. Now I am doing the same. Intersection I'll keep and I'll combine these two. A infinity intersection with minus infinity A. I can write. Now I have clearly told you while explaining the property, when you're going to take intersection of those like A infinity intersection with that, you're going to get null set. That is, there is no common element between these two sets. So that is the reason I can write this as null set. So when you're going to take intersection with null set, you're going to get null set again as per the properties of set. So when you're going to take interval of In complement, intersection of In complement and In double complement, you're going to get null set. Clear? Now I can write M star of In open interval In as M star of In complement union In double complement, right? See here, In complement and In complement I have assumed. So In will contain both the In complement and In double complement. So that is why I have written this. So I can take measure on their union. Fine. Now M star of In is none other than length of In. Clear? Length of In, or else let me write once again, M star of In is none other than length of In. This will be, I can split the measure inside so that I will get M star of In complement. When you're going to split, union will become plus. So M star of In double complement. Clear? Now look at equations A and B. I'm going to add equations A and B. Fine. Why? Because I am using this in this concept. A and B I am going to add. Let me see that. When you're going to add, you're going to get M star of A1 plus M star of A2 is less than or equal to summation n is equal to 1 to infinity length of In complement plus summation n is equal to 1 to infinity length of In double complement. Clear? Now after adding, what you're going to get is, I can write this as length of n is equal to 1 to infinity length of In complement plus length of In double complement. I'll just merge the value. Now just now I have proved that length of In complement plus length of In double complement, I can write this as length of the overall interval In, which is less than or equal to length of In. Fine. Now what I have assumed is, look at the equation 2. See here, from equation 2 what I have assumed is length of In is less than M star of A plus epsilon as per the property of translation invariant of outer measure. So I can replace length of In as less than M star of A plus epsilon. See here, length of In I'll replace it with, from 2 I can replace this with M star of A plus epsilon. Let me do that. M star of A plus epsilon. Fine. So what I have obtained is M star of A1 plus M star of A2 is less than M star of A plus epsilon. Since epsilon is arbitrary, I can neglect this so that I can write M star of A1 plus M star of A2 is less than M star of A. Let me rearrange this term so that I am going to get, since I have less than or equal to here, I can carry the same sign. I will just rewrite this. M star of A is less than or equal to M star of A1 plus M star of A2. Clear? Oh, I'm sorry. Since I'm reversing the inequation, right? So this will become greater than or equal to something like A less than B. I can write this as B greater than A. So that is why I have written this. Now let me replace the values of A1 and A2. That is what I have assumed in the given problem. See here, A1 I have assumed as, A1 is A intersection A infinity. A2 is A intersection A infinity complement. So let me replace it. M star of A intersection A infinity plus M star of A intersection A infinity whole complement. Now you can see that this satisfies the definition of measurability of a set. So this implies I can say in place of E I have A infinity. This implies I can say A infinity is measurable. But remember, this does not complete the proof. What I have proved is only, this is the proof of required lemma, that is A infinity is measurable. What we have proved is any open interval is measurable. That is what I have proved, right? Now, let me go for the proof of the required theorem, but what we have to prove is every borel set is measurable. Let me prove that. Now, coming to the proof of theorem, what we have proved is, let me write, we have proved, or else I can write, therefore, A infinity is measurable, right? So, let me write once again, therefore, A infinity is measurable. A infinity is measurable. Implies, I can write any open interval, since I have proved this for infinite case. So I can write for finite case, it is obvious. So I have already told you at the beginning itself, any interval AB can be expressed as like this, right? So let me write it once again, minus infinity B intersection A infinity. So this is also measurable, I can say, that just by the above lemma, since I have proved the interval is open interval A infinity is measurable, in the same way I can prove this is also measurable. So this is already proved. So their intersection is also measurable, I can say. This implies that what is the meaning of the statement open interval AB is measurable? That is, every open interval in R is measurable. Fine. I have already proved the theorem that any open set, if any open interval is measurable, any open set O, I have told in the property that A, right? So A is subset of union I is equal to 1 to n, I have told. So now I am going to take open set as O. So I can say any open set O is equal to union of I is equal to 1 to infinite of all the intervals. That is countable, I can say, countable union of open intervals. Countable union of open intervals is also measurable. Fine. What I have proved is any open interval is measurable, and further countable union of all the open interval is measurable. I have proved this theorem. Why? Because open sets can be expressed as countable union of all the open intervals. Open set can be expressed as countable union of all the open intervals. Since all the open interval is measurable, I can say this open set is also measurable. Now, I have told you in sigma algebra, mu contains, what I told, in sigma algebra, mu contains all open sets, right? Open sets in R. Fine. Since B is the smallest sigma algebra containing all these open sets, right? B is nothing but borel set. Borel set, what I said in the definition of borel set, it is the smallest sigma algebra generated by all the open sets. Since I have proved all the open sets is measurable, I can say B is also measurable. That is, all borel sets are measurable. Proof of this theorem is very simple, but you need to prove the lemma. Go through the statement once. I have given. What I have given is I have to prove every borel set is measurable. Borel set in the sense a smallest sigma algebra, members of smallest sigma algebra generated by all the open sets. Now what I have to prove is I have to prove that first all the open set is measurable. I have to prove. So let me take A infinity is a measurable set. I have to prove this as per the definition and as per the properties. I have arrived that all the open set A infinity is measurable. Now using this lemma, I can write open set can be written as intersection of this open interval. Fine. Since I have proved A infinity is measurable from the above lemma. Fine. If this is measurable, I can in the same way I can prove this is also measurable. So their intersection will also measurable. So meaning is all the open set is measurable. Further, I can say all the open sets is expressed as countable union of all the open intervals. Since all the open interval is measurable, since sigma algebra contains all the open sets, right? Therefore, B is a measurable. B is none other than measurable set. It is the smallest sigma algebra generated by all the open sets. If all the open sets is measurable, I can say B is a measurable set or borel set is a measurable set. Hence the proof. Hope it is clear. In the previous session, I have clearly told you about Lebesgue outer measure. Remember, there is a lot of difference. So, Lebesgue outer measure is denoted by M star. Lebesgue outer measure is different and measurable set is different. So, we call measurable set as Lebesgue measurable set. Lebesgue measurable set. And this as Lebesgue outer measure. Fine. Now the next concept is Lebesgue measure. Lebesgue measure. So Lebesgue measure is none other than it is a restriction on outer measure. Restriction on outer measure. In the sense, generally, suppose if I have any set E, generally how you are going to represent Lebesgue outer measure as M star of E. A restriction on Lebesgue outer measure is Lebesgue measure, and it is represented by M of E. We are not going to write star here. So since we have a restriction on outer measure, so instead of representing M star E, I am going to write it as M of E. Fine. This is what the Lebesgue measure is. Now, based on this, I have a theorem. Let me prove the theorem. And here is a statement. It is important asked in the year 2018. Fine. Statement is E is measurable and for any y belongs to R, then E plus y translation of E by y. E plus y is none other than translation of E by y is also measurable. Or else I can say, where we have proved in the previous case M star is translation invariant. Here we are going to prove M is translation variant. M is translation invariant. In case of outer measure, what we have proved is M star is translation invariant. Here measure M is translation variant. Fine. It is asked in year 2018 and 2019 also. E is measurable. Any y belongs to R, then E plus y is translation of E by y is also measurable. In the sense, translation invariant I can say. Fine. Now let me prove this. What is the given data here? Given E is measurable. Given that E is measurable. Fine. So, then I can write, while explaining the properties itself, I have told you, suppose if any number I am going to take in a real number, that is y belongs to R, I can write E plus y as some x plus y such that x belongs to E. In the sense, when I am going to add any element in E, like if x is an element E, x is an element in E, if you are going to add y to the set E, it is equivalent that adding that particular element in this set. In meaning is, suppose if I have set E, I have an element x here. So if you are going to add with the element y, it is enough to add the elements of E to this y. So that is what I have written. Fine. Now, since E is measurable, I can apply the property, definition of measurability of a set. What it says, if E is measurable, then there exists a set A which is subset of R such that M star of A is equal to M star of A intersection E plus M star of A intersection E complement. This is from the definition of measurability of a set. Let me take that as equation 1. Fine. Now we know that M star, we have already proved this. M star is translation invariant, right? Translation invariant. Translation invariant meaning is, when you are going to add any other element to this property will remain same. In the sense, suppose let me take say element y belongs to R in a real number, then M star of A plus y, in the sense if you are going to add any element to this, it doesn't change. So I can write the above equation as plus y. Just I am adding element y to each and every set associated with this particular measure. So M star of A intersection E complement plus y. Clear? Why? Because I have already proved M star is translation invariant. Then I can add any element to the set associated with M star. So it doesn't change. So that is what I have done. I have added an element y in a real number R to the set A. So I have done it for each and every element. So let me take this as equation 2. Fine. And now if any element x belongs to this set, let me take this set, A intersection E plus Y. Fine. So then that implies, since I am taking intersection, I have to write the second set. X should also belongs to E plus Y. Fine. Now let us take any element, say Z belongs to A intersection E. Suppose in this set I have an element Z. Then I can write X belongs to Z plus Y. Fine. Why? Because Z is A intersection E. Z is the element which is in A intersection Y. Then Z should be in this set, right? So that is the reason I can write X belongs to Z plus Y. So here what I have assumed is Z belongs to A intersection E. Meaning is Z belongs to A intersection is none other than common element. So Z will be in set A and Z is also in set E. Fine. So I can write X is equal to Z plus Y as it belongs to A intersection A plus Y. And I can write X belongs to E plus Y. Fine. Meaning is Z is in both A and E. So that is why I have taken X as Z plus Y as it belongs to A plus Y and as it belongs to E plus Y. As Z belongs to both the sets A and E, I can write like this. Clear? Meaning is I can write X is in the set both A plus Y and E plus Y. A plus Y, both in the sense I can take intersection E plus Y. So let me take this as equation, say B. Let me take this as equation A. Now from equations A and B, I can write that, see here, A intersection E plus Y, as X belongs to this and X belongs to this, I can equate these two sets. Why? Because this element is in both the sets. So I can say these two are equal. A plus Y intersection E plus Y. Similarly, let me replace E with its complement, E complement. So I can write this as, wherever E is there, just change to E complement. Clear? So I have taken an element and which says Z, which is in this set. If that was the case, I can write like this. So from these two assumptions, I can say these two are equal. That is equation A and equation B. RHS are equal. LHS are equal. Yeah, I can equate RHS. So that is what I have done. Now by above property, what I did is replacing E with E complement. I have obtained this. Fine. Now I am using these two in equation 2. So with this, equation 2 becomes LHS as it is, that is M star of A plus Y. Now let me change RHS, where I can change, see here, this value I can replace with this, that is M star of A plus Y intersection E plus Y. Clear? Plus M star of this value I can replace with this, that is A plus Y intersection E complement plus Y. Is this clear? Hope so it is clear. Now what I am going to do is replace A with A minus Y. Wherever A is there, I am going to replace with A minus Y. So when you do that, A minus Y plus Y get cancelled, you are going to get M star of A. I am going to write directly. And similarly, when you are going to replace Y with A minus Y plus Y minus Y, I am going to change this A minus Y. Minus Y plus Y get cancelled. You are going to get A intersection E plus Y. Fine. Plus M star of the same thing you are going to change here. You will get minus Y plus Y get cancelled, left with A intersection E complement plus Y. Clear? Now look at this statement. From this statement, it is from the definition of measurability of a set A. So if any set is measurable, I can say this definition, right? So in place of E, what we have? E plus Y. This implies E plus Y is measurable. Therefore, I can say measurability of E plus Y can be written as outer measure of E plus Y. So if this holds, I can write, when measurable property of measurability holds good, I can write measure of E plus Y is equal to M star of E plus Y. Since Y is an arbitrary element I have chosen in the real number, I can write M of E is equal to M star of E. That is, M is translation invariant. Fine. Just I have applied the property. Please go through once. Hope so it is clear. Continue in the next session. Thank you.